So today we're having a talk from Sven Banisch, who's from the Max Planck Institute on Mathematik der Naturwissenschaften, so mathematics and science, indeed, in Leipzig, where he's involved in two research groups, or two that are, I think, relevant for this topic. The one is the general theory of complex systems, and the other one is on economics and social sciences. And he's also working on this Odysseus opinion dynamics and cultural conflict in European spaces horizon project of the EU. And today he'll tell us a little bit about social feedback theory. So please go ahead.
Yeah, so thanks a lot for this invitation and giving me the chance to talk a little bit about one theoretical framework in which we model opinion dynamics within Odysseus, within the Odysseus project. I think usually I make an introduction to the project, but today I really want to focus on this idea of modeling collective phenomena by feedback of others. And so, but I want to say that in the project there are also two groups from Amsterdam, actually, which is the group of Justus Uitermark in sociology and Richard Rogers from the Digital Methods Initiative. So I happened to visit Amsterdam quite frequently before Corona was stopping all these. So this is work in the Odysseus group in Leipzig with Eckhard Olbrich, Felix Geisbauer, and Armin Pornacki. The latter two are two students in our team. And as I already said, I find it quite interesting what you have founded here with the DIEP, and I just wanted to start somehow my talk today with providing at least a little perspective of how emergence is also at the core of sociological thinking and very important in this area of research. And I think there is a book that I have with me since quite some time now, which is called The Micro-Macro Link, to which very prominent sociologists actually contributed chapters on studying the relation of the micro and the macro. And this is shown here, and really I can recommend this to get a little bit the tradition of thought in sociology on problems of emergence. Just at a very general level, to illustrate how emergence comes into play, or micro-macro comes into play in sociology, we can think of three core areas of interest, which is on the one hand social structure and networks, on the other hand culture, and then of course usually we sociologists develop some theory of action relating to individual behavior at the micro level. And in my understanding, at least, emergence relates mostly to the micro-macro link from individual behavior, collective individual behavior, to certain macroscopic patterns, which may be emergence of power structures in social networks, or it may be more related to opinion dynamics or cultural dynamics, where we study how cultural diversity is maintained, for instance. But in sociology, there is a lot of this discussion whether emergence is enough to characterize the relations between micro and macro, because usually things at the structural level are called structural because they structurate individual behavior. So think, for instance, about roles in which you might find yourself in certain social situations. And these roles are certainly established by some kind of emergence from social interaction, but then they feed back into the way people behave. So we really have a feedback loop, a two-sided feedback loop from micro to macro, And I think several traditions of thought on emergence, they can somehow be related to studying one specific link or discussing the relation of this feedback loop, so to say. I don't know how is the general mode for presentations in this round here, but I would say if you have some questions, just ask in between. So what I will do today is I will very briefly look into the field of opinion dynamics and then introduce the social feedback theory. And then the main part of the talk will be on two models, one for polarization and one for collective opinion expression and silence. And I will finally briefly discuss Twitter as something that we have in mind in terms of empirical application of these theoretical ideas. So opinion dynamics is a field that develops theoretical models of collective opinion processes to understand basic mechanisms behind the emergence of consensus, polarization, and conflict. And there is, since I would say more than 20 years now, there are many, it's a quite active field with many different mechanisms proposed. And I want to somehow give a little bit the basic motivation within the field to test different mechanisms, especially for polarization dynamics or persistent plurality. So early mathematical models emerged in the 50s, 60s out of an interaction between mathematicians and psychologists, actually. And the question was basically related to consensus formation processes. So given a group which somehow has mutual influences, which is captured by a matrix A, which is usually normalized so that it's row stochastic. So this is, we have such an influence matrix, and what we want to study is, given an initial opinion profile at time 0, how does the system evolve when these influence mechanisms are repeatedly applied on the agents? And most of these early models are linear models, which means that it's just the new opinion profile of the system. So O is a vector of opinions of n individuals. So the new profile is given by the product of the matrix to the previous opinion profile. And this means that we can study the convergence of such a model just by looking at the powers of the influence matrix. And this matrix, so we know well from linear systems and Markov chain theory that whenever this matrix is connected, so whenever it consists of a single connected component, then this matrix approaches a limiting matrix, telling us that in the end, the final opinion profile is just equal for all the agents. So this is basically the setting which is at least at one source of modeling opinion dynamics. And the question somehow emerged when these models predict consensus in any case when the network is connected. So what are further ingredients that we need to model persistent cultural diversity, persistent plurality, and polarization? What is, of course, a big advantage of these models is that they are analytically tractable, and we don't have to rely only on simulations in their analysis. However, when we include further ingredients, usually we lose this this ability to analytically formulate and analyze the model, because we introduce non-linearities. We introduce, when we go back, we introduce a certain dependence of the influence weights on maybe the opinion distance and so on. And so usually the mathematical formalism is not any longer applicable. Now, the question thus emerged, how does a population with moderate initial opinions diverge into groups of agents that strongly support opposing views? So, and within the project Odysseus, I mainly follow two ways of modeling such processes. About the left one, opinion polarization by learning from social feedback, I will talk today. But I just want to notice that there is another route to modeling, which is based more on a deliberative idea of argument exchange. And I wanted to highlight that I just managed last week to have a new preprint on bias processing, which relates this model to an experiment on argument persuasion. And I find, well, I'm honestly proud of this study, because it's really a step in opinion dynamics, I think. So, but today we talk about social feedback theory, and this is a very simple modeling framework, actually, and it's based on the idea that humans are sensitive to social approval and disapproval. So usually when we meet other agents and they support our opinions, then we feel good. And when they challenge our opinions, we feel bad. So this is the basic idea. And this means opinion expression is treated as an action that triggers feedback from a social environment. And this is something where, in terms of modeling, we depart from most previous models by really modeling or differentiating between an internal opinion and an opinion expression action. So this feedback leads to a new evaluation of the different options for communication. And this new evaluation is mediated by the reward signal. So we get a reward, and then we implicitly judge how good this expression has been given my social neighborhood. So if we a little bit more formally, maybe this runs down to a coordination game, where here we see two agents that have two possible opinions that they can express, red and blue, and they have an internal evaluation of these opinions. And when they engage in interaction here, they just, we model this social approval, disapproval dynamics by providing positive feedback if they agree. So if they both articulate red or both articulate blue. And if they disagree, they get a negative reward. And now we, this is played over a social network. And so opinion dynamics is conceived as repeated games that agents play within a social network. And agents adapt by learning from the feedback that they obtain by peers. And in a sense, as we will see, agents solve the collective game by methods of reinforcement learning. And this means that we can apply game theoretic concepts in the analysis of the model behavior, which somehow saves back a little bit the analytical tractability problem in opinion dynamics.
May I ask a question?
Yes.
So what's the relevant attitudes and is the relative distribution which behavior to show or something, and then they pick one? So the associated behavior is not actually their opinion, but just sort of one realization of a distribution.
I don't hear you. I don't hear you perfectly, but when I understand correctly, you ask about this distinction, so to say. I think it will.
Yeah.
It will come out later a little bit more explicitly, but the basic idea is that what we do when we interact on opinions, especially when we interact on online platforms, we have certain actions to articulate our opinion. And this is what I call behavior here, because we have to behave to make things visible to others. But of course, we also we carry a whole, let's say, a cognitive backpack with us, and this will somehow determine the way in which we behave in this communication arenas. Here I make a very simple, a simple model where I just say, okay, all this complex internal cognitive configuration is just one evaluation, which determines whether I will take an action or not. But of course, one can go at a higher level of complexity in terms of the cognitive internal structure. And this is actually what we do with this other modeling paradigm of arguments. So there we really want to go to the cognitive level of content also. Is it okay?
Yeah.
So I just want to show a little bit in terms of this micro-macro divide, what is the meta model behind this theory, and what it can do in these terms. I think the social feedback theory is especially suited for analyzing the effects of social structure on different collective regimes of opinion expression, or different collective opinion phenomena. And it is modeled by this idea of learning in opinion games. A brief remark on this learning may be at place here. So because we will use a rather well-known reinforcement learning scheme as a behavioral model, and reinforcement learning is actually well established in psychology, and of course you probably know it from machine learning algorithms. But there's also a sociological thinker, George Homans, who proposed social exchange theory, which heavily draws on ideas from reinforcement learning. And here we have a statement: for all actions taken by persons, the more often a particular action of a person is rewarded, the more likely the person is to perform that action. So this summarizes what we want to model with this kind of learning mechanism, and we transport somehow these ideas into the area of opinion dynamics to study opinion expression behavior. More recently, the mechanisms of reinforcement learning have seen some justification in terms of social neuroscience and processes that are at work in the brain. And this research arena, I don't know if someone of you is a little bit into it, but it basically aims to identify neural mechanisms that are involved in the processing of social information. And here it has been quite some discussion whether humans have evolved somehow a specific circuity or a specific architecture for handling such social information. But what seems to pop out of this research on social neuroscience is that a basic reinforcement circuit is at least strongly involved when we get social rewards on our interaction decisions. And in particular, temporal difference reinforcement learning has provided a very useful computational account because it has this nice property that the firing rate of dopamine neurons can be related to this entity. But let me briefly explain the main idea of well, the most simple scheme of reinforcement learning, which basically is a dynamics on what I call Q here, and Q is the evaluation of an action. So Q encodes a subjective expected reward for an action that can be taken. And for any actions that we have or behaviors that we have available in a social situation, we have such a Q value, and we adapt it by means of this temporal difference scheme. And this works as follows. So we assign a new value at t+1 to this evaluation by adapting the current value with the product of a learning rate and a temporal difference error. So the temporal difference error is basically the difference between what I expected from my behavior and what I get. So, and exactly this difference has been shown to be related to this firing rate of certain dopamine neurons, especially here in this green areas. So what we can, I think, say is that when we want to model collective phenomena, it's really fair to base our model on something which is like a very basic mechanisms that social neuroscience has provided some justification of. So I would approach to the first model. So it's a model of polarization. But if there are questions, I'm happy to address them now. Okay. So this model, it was the first model on social feedback, and its aim was mainly to provide a really simple answer to this puzzle of polarization. So how does a population diverge into a bimodal opinion distribution? And as already said, we assume that agents can express two different opinions within a social neighborhood. And on expressing their opinion, they receive a confirming or non-confirming response depending on the opinion of a neighbor, of the neighbors. So the assumption is that agreement leads to a positive experience and strengthens the conviction and the evaluation of this expressed opinion. So opinion expression is taken as an action, and as said, by Q learning, agents learn the values of actions based on the reward that they get on expressing them. And I just note here that this can, of course, model different kinds of feedback. And if we think in terms of social media platforms, probably the sheer number of feedback or retweets or likes and so on is a really strong signal of feedback. But I will remain completely in the setting of dyadic interaction here. So we have pairwise interactions. We draw two agents and play the game. And so it's a very simple reward system that we use. For agreement, we have a positive reward of +1, and for disagreement, a negative reward of -1. And the process is that we choose a random agent, and this agent expresses its preferred opinion. So the opinion that where Q is maximal. and we have some exploration here. So sometimes they deviate from this maximum. And then we draw a random neighbor of I, and this neighbor responds with its opinion, and then agreement and leads to a positive and disagreement to a negative reward. And then we update this internal evaluation by Q learning. So I hope that it works. Please tell me if you don't see. Do you see this? So this is basically referring to a page where I try to somehow launch some models. And what I want to show here is just what I just introduced, the mechanism I just introduced on a network that is actually very prominent in network science, which is the Sarahi Karate Club network. And here it's a really nice study actually from the 70s, where the author somehow followed a karate club during a period where it was actually splitting. So there was a conflict of the president of the club and the instructor of karate, who had different ideas how the club should behave, what concerns the fees of the members, and so on. And the network is derived by really looking at who was sharing situations with whom in different contexts. So it's an empirical network. And now, just to illustrate the model, we have here a red node and a blue node, which is the president and the instructor, and they have different opinions. And now we look at what happens when we apply the mechanism. And what we see here is that we have basically two clusters emerging, which now evaluates into just one. So this is the example that I didn't want to see, but doesn't matter. But what we basically see is that in the process, agents emerge a higher conviction, highly support one of the two opinions, and whether they support one or another is basically determined by how connected they are within the system. So let me just give a rerun of this model. Yeah, I think what I find actually nice about having this online seminars is that participants usually have opportunity besides at their computers to just play with the models, and I invite you to just try this, let's say also this one here, to get a little bit an intuition about what I'm introducing here. So so what I was basically using as an underlying network to have let's say the main to crystallize the main dynamical characteristics of this model is the spatial random graph. And the spatial random graph is a structure where we somehow have a little bit a spatial clustering of nodes. So it's not just a random graph, but it has some kind of spatial clustering. And the main idea is that we distribute endpoints in the unit square and link them if their distance is below a threshold. So this is the kind of networks that we draw here. And what we see and what we have seen in the demonstration is that we have a relatively quick process in which certain structural groups coordinate on one opinion, and then we have a reinforcement process where the conviction in this opinion increases. And conviction here, or opinion extremity, I call the value difference. So how much is expressing white preferred over expressing black, and vice versa. So it denotes the strength with which an opinion is supported. And I talk about polarization in the sense that agents become more and more convinced of opposing opinions. So what we see here, if you look at the distribution of these value differences, we see really the emergence of two opposing opinion camps. And of course, we can look at this in terms of certain macroscopic observables. And the main ones are somehow the mean opinion and something called dissimilarity or the variance. And here we really see that the mean opinion remains at close to zero, but of course we have this emergence of a bimodal distribution where agents concentrate at the extremes of the opinion scale. Now let's have a closer look onto the phenomenology of the model. So I depict here the time evolution of the Q values for two selected agents in this network here. So one is 29 and the other one is 69. And what becomes visible for the first agent is basically that. Do you see this here? Do you see your faces actually? Sorry.
No, we don't.
Okay, so I was just wondering because I have to put this window where I see you aside to see my slides sometimes. But anyway, so I show here two trajectories of Q values for individual agents. And what I find interesting is that it really models or may model a certain period of indecision for agents where they just switch back and forth between the opinion that is more valuable given the neighborhood. And because the neighborhood also adapts this makes a really a complex dynamics actually. But what we can see for this agent here is that it relatively quickly coordinates with his group on the red opinion, and then it really takes off. So the red opinion is largely preferred over the blue one. Whereas 69 is an agent which somehow is at the interface of different groups. And here we observe that he just approaches or adopts the red opinion in a certain period of time, but then as neighbors adapt and a certain part of the network is invaded by the blue opinion, he has to readjust his opinion and will turn blue afterwards. So we have opinion switching for agents at the interface, and now the question somehow is how can we characterize the stable outcomes of the model when we have on the one hand side we have a quick process to achieve coordination within structural groups, which is followed by a process of reinforcement of the group opinion. And then polarization, of course, happens because groups coordinate on different opinions and become more convinced of opposing views. So this is basically the way in which the model creates polarization. And now, what can we do to characterize the stable outcomes of such a model? And here,
Can I ask a question of clarification?
Please, sorry.
In your model, during the iterative process, nothing is changed in the topology of the network.
No, it's fixed, yes.
It's fixed, so there is no influence like weakening connections or breaking connections.
Yeah, we think actually a lot about this. And one simple way to include this here would be to learn how beneficial it is to interact with a certain neighbor. But if we do this, then the network will get completely segregated. So the groups will completely segregate, and we think this is not really the most realistic thing. But you're right. I mean, now I'm just focusing on a fixed topology, and the question of how rewiring takes place and how co-evolutionary dynamics of networks and opinions takes place is, of course, a very interesting one.
Okay, I just want to know, because many people in our neighborhood have seen alternative models where the topology is changing.
Yeah.
Please go ahead.
Yeah, thanks. So on the static networks, and this is here important for the mathematics, then of course we can use the fact that we have a game theoretic relation, at least through reinforcement learning, because especially temporal difference reinforcement learning is known to converge to the expected payoffs of the collective game. So agents, in a sense, solve a game. And now what we can do is to characterize the stable profiles of the model, so the stable outcomes of the model, by analyzing which configurations satisfy certain equilibrium conditions. And the most well-known condition is, of course, the Nash Equilibrium. And here the main idea is that no individual alone is better off by switching to the other opinion. And this leads to the notion of cohesive sets, which mainly is that given an interaction graph, can the node set be partitioned into two groups such that each node has a majority of neighbor in its own group. So if each one has a majority of neighbors with the same opinion, then this is a stable configuration. And I show here a simple example where I have two agents, A and B, which have in the background a community of like-minded others. So both here have four neighbors with the same opinion, but of course A and B are linked and engage in interaction. And when we look at the payoffs of this game, then we see that the option that is most beneficial for both agents is to just stay with their opinion. So this is, in a sense, explains how polarization is sustained, and cohesive sets, cohesive p-partitions of networks really provide a precise structural condition for the existence of polarized configurations. Now, just to show how the Q-learning dynamics actually converge to these expected payoffs, I have here a related example where B is connected to 2 like-minded others and A is connected to 10 nodes. And what we can plot here is basically the expected payoffs of the game and the dynamic evolution of the Q values. And we see that there is a quick and good convergence to this. So this is mainly to illustrate that the game theoretic arguments are actually suited to understand this dynamical process, which is more a process of bounded rationality. So I will not go very deep here, but I'm also exploring another random graph model, which is basically a two-community stochastic block model, or a two-island graph, where we consider two communities, M and L, of agents which are strongly connected with a certain probability, 1 minus P, and there is a weak probability, P, to have links that span across communities. And in this graph model, we can compute somehow the probability that this configuration that we set is satisfies this cohesive set property. So we can compute the probability with which this is a cohesive bipartition of the graph. And when we do this, we come to the solid curves here, which is the probability that the graph consists of these two cohesive sets. And we can relate to this the results of the social feedback model, and we see a rather good approximation here. So so this is based on simulations where we initialize the system in a polarized state, and we analyze whether this is a stable state under the dynamics of the model, and then we compare this to the theoretical probability of having a cohesive bipartition. So Janusz, what is my time horizon?
Yeah, so I would say approximately another 20 minutes.
Shall we take a 2 minutes break?
Yeah, we can do 2 minutes of stretching or something like that.
Yes.
Okay.
So I will already give you the next slide that you can start to read if you want, but then I will be back in 2 minutes.
Okay. See you then.
Okay, let's go on. So now I want to come to the second model, which is a model of opinion expression and silence. And this model is motivated by a communication science theory, which is called the spiral of silence. And it's a theory which is, in a sense, quite influential in communication sciences, but it's also not always so well received somehow. But nevertheless, I will illustrate the main ideas. So basically, it's based on the idea that people experience a fear of isolation, and this fear of isolation goes already back to John Locke in the 17th century. And for this reason, people constantly monitor the behavior of others in their surroundings, and noting opinions and modes of behavior that meet public approval and disapproval. So here again, we have this idea of approval and disapproval. People refrain from publicly stating their position when they perceive that this would attract and raise objections. Conversely, those who sense that their opinion meets with approval tend to voice their convictions fearlessly. So what this somehow leads to in the end, and we are here now, is that the actual strengths of different opinion camps does not necessarily determine which view will be voiced, will be dominant in public. Even if the majority of the population holds the opposing view, one can have a very loud minority, which by which agents in the majority just receive or perceive that their opinion is not the majority one. So it models a spiraling process whereby a dominant camp becomes ever louder and more self-confident, whereas the other camp falls increasingly silent. So I just want to note that this is, of course, a theory that has been developed in the 70s, and it has been developed in the context of elections in Germany, where usually people were asked in opinion polls, whom would you vote if next Sunday were elections? And Elisabeth Noelle-Neumann somehow found that it's more predictive and more sensible to ask, what is your expectation? Who would win the election at next Sunday? So she really asks for these expectations, which mimics somehow what people perceive in their social environment, what signals are around that somehow signal the prevalence or the dominance of one party over the other. So now we consider that people have settled on two different opinions. So here, for illustrative purposes, I have a US politician retweet network from this platform Twitter Politics, which is actually launched from the group in Amsterdam, in Odysseus. And what we ask is, what are the mechanisms by which groups with certain opinions gain public voice and force others holding a different view into silence? Now, this has been published in Physical Review E just, I think, last year. And it's mainly a work of Felix Geisbauer, who is a doctoral student at our group. Now, as said, we consider two groups that have competing opinions, and now agents can choose to express their opinion or to remain silent. So the action is a little bit changed. They don't change opinion anymore, but they decide whether the opinion they have is worth expressing in a social neighborhood, or whether it is better to be silent because it will be rejected by neighbors. So again, agents receive supportive feedback from their in-group and negative feedback from their out-group when they express the opinion, and they receive a reward of 0 if the neighbor is silent. What just as a side note, maybe what I found very interesting, I was talking to one of my neighbors some weeks ago about Corona related issues of opinion, and she was telling me that it's so heavy at this time, because anytime she meets with some persons, she has to carefully assess whether this person is pro or contra the Corona regulations, and has to decide then whether she brings up the topic or not. And so she really articulated to me that she is having this sensing of the opinions of others, and trying to adjust their behavior of opinion expression on this grounds. Now, in this setting with this reward system, again, we use the usual reinforcement learning method, by which agents evolve an expectation of how rewarding it is to express their opinion. We also have to include a model of action selection, where we here take just a softmax scheme, which notes that when it is when the subjective expected utility Q for expressing my opinion is larger than 0, there is a high probability that I will articulate the opinion, but it's not a strict max, it's a soft max. And again, this encodes the idea that for all actions taken by persons, the more often a particular action is rewarded, the more likely the person is to perform that action. And the more valuable to a person is the result of his action, the more likely he is to perform that action. So it's really this reinforcement feedback loop that we aim to model. And so this is just a summary of the micro assumptions. Important here that we set the value of silence to 0, because the reward is always 0. But this allows somehow that we can have a efficient aggregation in a mean field type way of the model dynamics if we make a structural assumption. So again, here we study 2 groups, and we assume that we can characterize these 2 groups in terms of size and connectivity. So in terms of in-group cohesion, so the probability that a link within the group is created, and the probability that links across groups exist. So we can derive 2 structural parameters that determine the probability of group interaction, and hence the expected rewards for members of the groups. And these parameters are just denoted as gamma and delta here, and we refer to them as structural strengths, because the higher they are, the more beneficial it is for members of that group to articulate their opinion. So what we can do is, when we have this discrete time reinforcement learning mechanism, where we learn somehow how rewarding it is to express my opinion given given the group setting, we can now somehow aggregate this with respect to the 2 groups independently, and derive an expectation on the reward for agents in the 2 groups, which depends on gamma and delta. And now with some limit in terms of letting the time step to 0 and the learning rate to 0, we can derive a 2-dimensional system of differential equations, where the update is just given by the the current, or by the estimate of Q for group 1 here, and here group 2, and the reward that is expected. So we can derive a closed system of equations by this assumption that the groups can be treated as homophilous. And of course, having such a dynamical system, we can derive a phase portrait of the dynamics, where we have here the value of expression in the minority group, and we have the value of expression in the majority group. And what I show here is just the simple random graph without actually any structure. So the interaction probability is just equal in between all the agents, but this minority is half the size of the majority, which means that gamma is 1/2 and delta is 2. And this leads to a dynamical picture in which only the majority expresses its opinion, which we see because the value of expression is above 0, but it's below 0 for the minority group. So this is the only fixed point of this model. And what somehow is the aim of this now is to study certain kinds of structural transformations that may lead to different regimes of opinion expression. And one of these transformations is that minorities somehow tend to organize themselves internally and try to establish a more cohesive organization. And if we can model this by just increasing the link probability within the minority. And what we see is a series of bifurcations in which additional fixed points appear in the dynamics. And in particular, when we increase the value by a factor of 4, here we have a completely symmetric situation where we have a fixed point where only the majority expresses its opinion. We have another fixed point where only the minority expresses its opinion. But we also have the regime, which I call here coexistence, where both can express their opinion. So what with a combination of these dynamical systems arguments and also game theoretic arguments, we can have a rather complete characterization of this model. And what I show here, I hope that I can somehow transport the message effectively. But what we see here is the available pure Nash equilibria of the game when gamma and delta vary. So increasing gamma means that we increase the strength of group 1, and increasing delta means that we increase the strength of group 2. And what we see here is that we have different regimes where we have different Nash equilibria available. And what I do here on the right-hand side is just to go to a specific regime and show a phase portrait in this regime. And in particular, here we have this situation where we have a stable fixed point where only the second group expresses, so this E here, and we have a stable fixed point where the first group is expressive and the other group is silent. And then we have here this unstable fixed point, which shows a little bit what is gained by having also a dynamical description and not just the game, because we can by this Nash equilibria, these 3 equilibria appear side to side, but under the Q-learning dynamics, of course, this SS, so silence equilibrium, is just unstable. So what I have shown on the previous slide was somehow a transition increasing gamma, so a transition from this to this, or better from here to here maybe. And what I just want to show finally on this model is a transition which somehow mimics the formation of echo chambers or echo chambering. So this means that we here increase the strengths of both groups at the same path, which means that we somehow create a situation where opinions or where the social structure is organized around opinions. And what we can do with the model is a bifurcation analysis. And what I find very nice about this is actually that the assumptions that we derived in order to mimic this spiral of silence theory can also explain the dynamics of echo chambering, namely because when we increase gamma and delta, so the strengths of the two groups, we make them more homophilous. Then these very mechanisms that can lead to silence will lead to the fact that both groups may express their opinion in their own spheres of expression. And this is, of course, motivated by certain structural transformations that become possible through different public or semi-public groups of opinion exchange in online social media. So I hope that it's not getting too much, but 1 hour is also something. I would like to spend let's say last 5 to 8 minutes on an empirical case, let's say, where we approach Twitter out of this framework of social feedback theory. But maybe there are also questions that might be asked now, or maybe you indicate me, oh, it's enough. I can also stop stop here. Otherwise, I would continue.
Yeah, maybe we can do 5 more minutes on the Twitter and then have some questions.
Yes. So this would be the plan. So
I have one more clarification question.
Yeah.
In the graphs, you were showing these yellow and blue lines, and you didn't tell them the previous ones. Yes.
Yeah.
Yellow and blue lines on the right.
Yeah.
Are these curves indicating optimal responses for one of the players groups?
Yes. So this is the isoclines of so the fixed curves, so to say, for the single groups. And of course, where they meet, we have a fixed.
There are the equilibria. Yeah. So you have here even more in the top right. You have even 5 equilibria.
Yes. We have 3 stable ones, which are these 3. Yes. But we also have these unstable ones here. Yeah. And likewise, here we have this unstable one in between.
Okay, thanks.
Okay, so so let me first of all maybe highlight that Twitter is one object of study that we address in the Odysseus project, and I just want to recommend to check also this web page where we have launched the Twitter Explorer as a tool where you can just look at current debates on Twitter and generate, for instance, these retweet networks. So it's a tool, you have to install it, but it's aimed at least to be an easy to install tool. So somehow my idea behind developing these social feedback models was basically that I think for online communication, it's very important to differentiate between an opinion that agents hold somehow, which is a latent structure, and the behavior that actually we can observe on the platform, which is usually the target of studies in computational social science or network science. And somehow I would like to have a model that explains what we see in the online spheres. And what this means somehow is a shift of explanatory focus from different forms of social influence to incentives and rewards that different settings or platforms provide on opinion expression. And so we are not there yet, because empirical data is always more complex than such nice, simple models, where especially we have only dyadic interaction. But I think some relations can already be made. So what the starting point for this Twitter analysis somehow was that retweet networks on Twitter typically show a strong community organization. And basically what we see here below is that in many events, when we use the Twitter Explorer to go to a current debate, we see two clusters of competing opinions emerging. And now we have compiled in the context of the state elections in Saxony just 2 years ago, we have compiled a data set where we somehow start from the most relevant political actors, local actors, to construct, let's say, a relatively controlled Twitter sample. And we use the retweet network to somehow color the agents according to the position they support. And we checked this manually and have like a rate of 95 out of 100, with which this is really a correct classification. So on the one hand, we have accounts that relate more closely to content of the right-wing populist party AfD. This is a smaller number of accounts, and then we have all the others in another cluster, and some of the conservative parties also appear in between. News outlets usually appear in between here, and what we wanted to know is, do these groups engage differently when they go to the comment spheres or to the reply spheres of Twitter? So what we basically do is that we use this classification that we can obtain from the retweet network and construct a network of replies where two agents are linked when they reply to one another. And what we find is a very different macroscopic pattern, which is not at all polarized in the usual sense. So there's really it seems to be a sphere of confrontation. And what I find interesting also in the larger context of emergence is actually that somehow retweets and replies, they serve different communicative functions. And these communicative functions lead to very different macroscopic patterns of interaction. And so for me, this is a very, I'm not through with thinking on that, but I think it's a very interesting, it's very fascinating for me, this to have this functional, I mean, reward-related differences reflected in stark differences at the macroscopic scale. So what we look in this Twitter study on this Saxony data set is basically what was one focus is to see whether one group somehow asymmetrically interacts with the other group in this reply arena. And what I show here, it's just a brief snapshot, so to say, is the majority cluster and the minority cluster, and the local associativity encodes to which group do they respond to their own group, or do they respond to the opposing group, so to say. And what we see is that for the majority cluster, most accounts predominantly respond to the majority cluster itself, so to the own group. But in the minority, we have a rather strong tendency of having accounts that respond more to the other group. So it's an indication of ideological asymmetries, and somehow how this could be represented in the model that I was just showing is that we have somehow a kind of asymmetric outgroup attack. So this is mainly to illustrate that given all these approximations that we make by homogenizing the two groups and avoiding heterogeneity of the accounts, still let's say general regimes of collective expression can become visible, and at least we can study the effects that such asymmetries may have on the opinion climate and opinion landscape. So what we see is that such an asymmetric relation may really change the picture, and may in particular lead to the case that the possibility for the majority or the perception of the majority may be distorted in a way that they think, okay, it's not worth articulating my opinion, because the increased activity of the minority group somehow leads to the effect that their opinion is perceived as prevalent. A similar, let's say, ingredient with which we can play in order to come close to these asymmetries is with costs, which may account for higher motivations in the minority group to engage in this reply spheres. Now,
experiments, did you observe the polarity of the messages, or did you just count them?
In this, you refer here to?
Yes.
Yeah. So we don't use content yet.
So it's just counting.
The only content that we somehow use is this classification based on the retweet network. But of course, this is when we think about in Odysseus is actually a very important aspect to combine the structural and the content. But I must say we are not that far yet, and also we don't want to do a too simple sentiment analysis or things like that, which are not really well. At least we are not always convinced of what is done with these tools.
Thanks.
So to conclude briefly, what I think I could show is that social feedback, or the first model has shown that social feedback is an efficient way of group coordination, and it may have evolved as such. So this is what social neuroscience in a sense suggests. But on large social networks, local coordination comes at the expense of global polarization. So this kind of social feedback may drive polarization dynamics. And in large networks, it's actually polarization is the rule rather than an exception. While social feedback is derived as a plausible psychological mechanism, one of the main benefits is that we can apply game theoretic arguments in the model analysis. And here in particular, the notion of cohesive sets provides a really nice mathematical condition for the stability of polarization. So somehow this is one of the objectives of the Odysseus project, was to somehow combine game theoretic arguments with opinion dynamics. And this is, let's say, one of the main contributions, I would say, of social feedback theory to achieve this theoretical link. We have seen that even strong majorities can be forced into silence if a minority acts cohesively, and that we find certain strategic exploitation of this dynamics. And we also have seen that retweets and replies on Twitter are very different and lead to very different macroscopic patterns of engagement. So if I would have to summarize all in one, I would, or if I have to give a message, maybe it is that seemingly innocent and largely unconscious feedback mechanisms and decision processes may have a tremendous effect on what becomes visible in the online world. So I thank you very much for your attention, and I hope you enjoyed this long talk a little bit. Thank you.
Yeah, thank you very much. Very interesting. Let's give a round of applause. So we've gone a little bit over time, but if there are any questions, we can go ahead. Anyone have any questions?
May I ask a question?
Yeah, go ahead.
I was wondering if you have thought of using this this modeling mechanism that you have to model, let's say, more high-level type of convergence, like instead of converging on the same opinion and things like that, of emergence of meta-agreement, for example, the type of mechanisms that result in, for example, the emergence of single peakedness and stuff like that. So where the agents do not necessarily agree, so it's not about looking at the opinions of the agents or about the dimensions or the relevant factors that the agents consider for forming their opinions.
Yeah, yeah. This relates more to having having content in the model. So let's say I think this is very important, and I think it's a main mechanism if we think about cultural conflicts. So we have certain representations and we have certain relevance structures, so to say, on which dimensions we make distinctions, or we see that distinctions are necessary. This is a little bit we approach this with this argument models. And if I look into what I want to do in the future, it's actually to achieve a combination of these tools. So having this social feedback mechanism where we act in having at the same time some kind of more complex cognitive architecture, which allows somehow to include more specific knowledge about specific debates.
Yeah, that makes sense. Thank you.
So I don't really understand, but
yeah. So Surush, your sound is very soft when you begin talking, and then your microphone sort of kicks in or something.
Can you hear me now?
it's very.
Can you just now? Let me just. Is it better? Well, I just said thanks very much for your answer.
Is it okay?
Yes. Thank you.
Okay.
So maybe I had a short question. I was wondering how robust the results are to changes in, for example, other aspects of these algorithms, the Q-learning, for example, the exploration rate and the learning rate and the selection mechanism and those things.
Okay, I mean, there are maybe it's important to differentiate here between the two models. The first model is very stable when it comes, for instance, to exploration. Okay. Because it's just exploration will lead to a quicker perception of all neighbors, but still the signal will be the same in a sense. In the other model, when we let's say exploration has a larger impact. So remember this isoclines that I showed on the stable profile, so to say. So if I take completely rational choice model, so this would mean that beta goes to infinity, then I have a really really sharp curves there. But as soon as I decrease the beta, which means that I increase the temperature and the exploration in the system, then these curves somehow smoothen, and so they may change the structure of the fixed points of the system here. So actually, it's something I in the paper in PhysRef E. I think we have one bifurcation with respect to beta, which we study there. But there it has a strong impact. So,
if I can contribute to the discussion, one comment: you are mentioning that you are using game theory.
Sorry, what?
You are referring to game theory, but it seems to me that you're particularly using evolutionary game theory. Would you agree?
Well, I think the reinforcement learning and evolutionary game theory is can be connected quite nicely, actually.
I think they are using the same mathematics,
yes.
basically.
But what, for instance, this plot where I show delta and gamma on all, this I would say is more a pure game theoretic reasoning for Nash equilibria, and also the notion of cohesive sets comes more from the theory of games on networks. So, but as I said, this game theory has no dynamics, so they are good to characterize certain conditions for existence, but we need the dynamical picture, which is, as you rightly know,
precisely what evolutionary game theory adds to the picture. Yes. Now, the more difficult one, in all your models, the basic opinion is single-dimensional.
Yes.
Is there any possibility, or is it feasible to extend the sort of analysis to more multi-dimensional spectra, where there are various issues at stake?
May I show something on that? So may I share my screen again just for 2 minutes? Because this relates really to the other kind of models that we study, which is this attitude structure models. Do you see this?
Yes.
So let me choose here. So there, I just want to show this because this is actually the core of the other kind of modeling that we have followed in the Odysseus project, which basically is that we have beliefs at a low level, and these beliefs somehow carry evaluative associations to issues, and in this case, it's even 2 issues. So what I study in this experimental paper is, for instance, different energy producing technologies like coal, gas, biomass, and arguments that speak in favor of these technologies or in disfavor. And what we do here is basically to say, okay, we have 2 issues like, let's say, coal and solar photovoltaic energy. And we have certain arguments that address only one issue, but we may have arguments that just treat the alternatives So these are then arguments that somehow connect the issues. So I might say that I prefer coal instead of photovoltaics because coal guarantees stable supply. So this is one of the arguments which would somehow upgrade coal and downgrade photovoltaics. So this is what we capture in such a structure, and what we study in this model is somehow given this argument or belief exchange mechanisms on two different issues, how become somehow the whole population, how does the whole population organize this into a collective belief system and into a collective system of attitudes. And what we see it's now just here is that we have a position on one issue, we have a position on a second issue, and they are coupled in a way that they somehow are opposing alternatives, and then we have such a negative correlation between the two opinions. So I would really be happy to talk about this more, but I think yeah.
But what's the mechanism here that provides the dynamics?
So the mechanism here is that we just have we also choose two agents at random, and they exchange beliefs. So let's say we choose one agent at random, and one of the agents articulates a belief, and the other agents can take it or not. And in the experiment that I was referring, we just explore this probability of taking or not as a function of cognitive coherence. But in this case, we have one constraint here, which is that what creates the bipolar situation here is that we have a homophily assumption on the attitude level. So we say that when two agents are very different in the opinion space, the probability of interaction is reduced. So this is the two things. We have argument exchange and this homophily. But likewise, when we have argument exchange and cognitive coherence, we can drop even the homophily assumption.
Thank you. Very nice.
Yeah, so many people expressed their thanks already in the chat and had to leave, and I'll thank you once again for sharing